Carl Ludwig Siegel, one of the great mathematicians of the 20th century from Germany, and he was visiting the Institute for Advanced Study in Princeton, giving a series of lectures, and one day it was a terrible snowstorm, like it was over the weekend, and nobody came into the lecture except Siegel hiked his way in because he was a hardy kind of guy, and he just looked out there, and there was no one there, and he just gave the talk. And the next time, people were confused because it was a series of lectures, and he was starting off at a place that was obviously not where he had left off. And they said, well, why did you give the talk, if there was no one there? He said, look, I came in, I was supposed to give the talk, I gave the talk, I went home, it was very systematic. Okay. So last time we did primes in Z of I, and showed there was a lot of relationship to number theory. For example, we showed that the primes congruent to 1 mod 4 gave rise to 2 primes, pi and pi prime, in Z of I, and primes congruent to 3 mod 4, 1 prime. In fact, the element p is still a prime. These 2 primes have the property that pi times pi prime is equal to p. So there was this nice distinction. And this is the statement, by the way, that if pi is equal to a plus bi, it says that a squared plus b squared is equal to p, which is a proof of Fermat's theorem that every prime congruent to 1 mod 4 is the sum of 2 squares. So hidden in this determination of the primes in Z of I, together with the fact that it was a principal ideal domain, we got that result. Yeah?
I just have a slightly unrelated question. Is there an algorithm to find the squares that make up
the A and the B? Very, very good question. So there are formulas for it. Gauss worked hard on finding formulas for A and B. In fact, you can normalize them. You see, one of them has to be odd. Right? I mean, you can't have two odd numbers adding up to an odd number, right? And so one is odd, and since you can change the sign of that, you can make the odd one either 1 or 3 mod 4 if you want to. You can normalize it a little bit, and then you can ask for an actual formula going from P to A, that sort of thing. And Gauss found such formulas, and people have searched for such formulas in the future. And I may even do a little of that in my special lecture next week. Okay? But it's a great, great question. I mean, once you prove it's a sum of 2 squares, it's like, well, what are A and B? Okay? It's related to another subject called elliptic curves, which I'm going to talk about next week. Okay? Now, what we're going to do for the rest of the term is we're going to study rings R analogous to Z of I, and determine what their primes are, although they're not always unique factorization rings. And we've seen some rings analogous to this. For example, in homework, there was this ring, Z squared to minus 2. So all things are the form a plus b squared to minus 2. And there, this delta function, delta of a plus b squared to minus 2, which is a squared plus 2b squared, this gives a Euclidean structure on this ring. So R is Euclidean with respect to this function delta. And so you have a nice prime factorization in that ring too. And then we also introduced the ring R, which was Z squared to minus 5. And that ring doesn't even have unique factorization, so it's certainly not Euclidean. No unique factorization, because we had 2 times 3 was equal to 1 plus the square root of minus 5, 1 minus the square root of minus 5. And each of these elements is irreducible, is a prime. So these rings obviously look similar, but they have different properties. So you might say, well, what we could do is a general analog of this was we could take rings like Z square root of D. That looks like a good example. So all things are the form a plus b times the square root of some number. And so that would be the same thing as taking the quotient of the polynomials in Z by the ideal x squared minus d. And if we wanted this to be an irreducible polynomial, we'd want d not to be equal to a square. So that all of these rings are of this form. Okay? Now, the reason, so we could study those rings, but this isn't quite right. This is not quite the right analog. Very close, but not quite the right analog of z of I. And I'll give you an example to show you why this is slightly the wrong thing to do. Because consider the polynomial f of x is x squared plus x plus 1. So the roots of that polynomial are alpha by the quadratic formula, minus 1 plus or minus the square root of minus 3 over 2. Okay? Now, if you take the ring R, which is z of x modulo the ideal f of x, this is a monic irreducible polynomial of degree 2. So this ring is z plus z of alpha. It's a free abelian, it has two copies of the integers, z times 1 plus z times alpha, alpha being the root of f of x. And any higher polynomial in alpha, alpha squared, alpha cubed, can be re-expressed in terms of alpha and 1 using this relation. Now, that ring contains the ring z plus z square root of minus 3. Because if I multiply alpha by 2 alpha, and I add 1 to it, that becomes plus or minus the square root of minus 3. So inside of this ring, I certainly have the expression 2 alpha plus 1, so I have a square root of minus 3. I also have 1, so I have this ring. But these two rings aren't equal because I cannot write alpha as an integer plus an integer times the square root of minus 3. I have to divide by 2. And in fact, this ring has index 2 in this ring. And both of them have the same fraction field. Our integral domains with field of fractions q square root of minus 3. The rational numbers adjoin the square root of minus 3. And obviously, we'd want to work with the largest natural ring we could inside of this field of fractions, which means we wouldn't necessarily want to work with this ring. It might be better to work with this ring. Anything that was an ideal for this ring would be an ideal for this, some ideals for this ring would not be stable under multiplication by this ring. So the preference is to always work for the larger ring. Sometimes can enlarge this ring inside the field of fractions. So the first thing we're going to have to do to figure out what the analog is of the Gaussian integers in this kind of setting is to figure out when we can enlarge it, what kind of rings we want to work with. It turns out, for example, that one reason that it's better to work with this ring is that this ring is a Euclidean ring. This ring isn't. So that was a big discovery that Euler made, that it was better to study the ring generated by this than just square root of minus 3. Okay, so we're going to back off a little bit before we tell you what the right rings are that we're going to study for the rest of the course, and let's talk a little bit about algebraic integers. I'll keep this up for a second. Now, I should say about the homework. So I've gotten a little bit behind to the schedule. So I had Peter change the homework on the web. You get a day off today just to sort of catch up, orient yourself, get ready for the final push. And then we're going to have 3 more assignments. One after class Wednesday, one after class Friday, and one after class Monday. And those are the assignments that Peter had posted, all moved back a day. Now, you may say, when am I going to hand in the assignment after class Monday if I'm catching a flight Monday afternoon? Okay, that's for you to plan ahead on. If you're going to be around Tuesday, hand it in Tuesday. If you're not going to be around because you're leaving directly after class on Monday, or God forbid, you're leaving before class on Monday, then you should try to get that homework assignment to Peter and Liz in some other way. Okay? They'll be gracious and take it in a little late. Okay, now, to get the right analog, we have to talk about algebraic integers. So we say a complex number is an algebraic integer. A complex number is an algebraic integer if alpha is the root of a monic polynomial f of x with integer coefficients. X to the n minus an minus 1, x to the n minus 1. Any monic polynomial. Monic means first coefficient 1, integer coefficients. Okay, so example. Every integer is an algebraic integer. Because an integer is the root of this polynomial. Okay, another example. Square root of d for d in z. Because that's the root of the polynomial x squared minus d. Like, that's an algebraic integer. Another example. This is an algebraic integer because it's the root of this polynomial, which is monic with integer coefficients. It doesn't look too integral, like it looks like it has a 2 in the denominator, but in fact it's the root of that polynomial. So these are all examples of algebraic integers. Okay? Now, we want to know if an element is a root of a polynomial with rational coefficients, is it an algebraic integer? So that's the first question. Suppose alpha satisfies f of x with rational coefficients. And let's assume that f of x is monic and irreducible. Namely, we find the polynomial of least degree that's satisfied by alpha with rational coefficients. Okay? And the question is alpha an algebraic integer? This will be an important thing for us to decide. Well, certainly if f has integral coefficients, it does it. But I claim that it's if and only if. Claim alpha is an algebraic integer if and only if the monic irreducible f of x with rational coefficients satisfied by alpha has integral coefficients. So you might say, well, how do you know that? There could be some other polynomial with integer coefficients that it satisfies. Just because it satisfied that one and that one didn't have integer coefficients, maybe there's some other one. But the answer is there isn't. So for example, this proves, example, 1/2 is not an algebraic integer. Is not an algebraic integer because it satisfies the following polynomial, which is monic and irreducible, right? And that polynomial does not have integer coefficients. In particular, any rational number that's not an integer is not. So, or any alpha which is in the rationals which is not an integer is not an algebraic integer. Another example. Alpha equals square root of 2 over 3 is not an algebraic integer. Proof? It satisfies the polynomial x squared minus 2/9 equals 0. And that's an irreducible polynomial, monic, but it doesn't have integer coefficients. So this is really quite good. It tells you things which are algebraic integers. It tells you things that aren't algebraic integers. Okay, now we're going to prove the claim. All right, let g of x be the primitive polynomial, well, maybe let's call it f0 of x. Polynomial over z with our irreducible f of x being its content times f0 of x. We can write any polynomial uniquely in that way, right? And this is the content. And here is our primitive polynomial with coefficients of the integers. And the content is a rational number. Okay? Now, alpha certainly satisfies f0. The problem is that f0 may or may not be monic. Okay? I claim that any polynomial that's satisfied by alpha over the integers is a multiple of f0. With g of alpha equals 0 has the form g of x is equal to f0 of x times q of x, where this is in z of x. Now, if I can prove that, that proves that statement. Because why? If f of x did not have, if f of x has integral coefficients, then f is equal to f0. Because the GCD of a coefficient is 1 because the thing was monic. Correct? If f does not have integral coefficients, then f is not equal to f0 because, in particular, this has integral coefficients. In particular, we've had to multiply. In particular, f0 is its leading coefficient, its first coefficient, is not equal to 1. Because f0 is a scalar multiple of f. If f0 were monic, right, it would be equal to f. So if f of x does not have integral coefficients, then f0 of x starts off with some coefficient like 2x to the n, or 7x to the n, or something of that nature. Well, any multiple of f0 would also start off with a first coefficient that was not monic. And consequently, any polynomial that was satisfied by alpha would not be monic, so it would not satisfy this condition. All right, so I claim, so we see that this is true if we can only prove that any polynomial satisfied by alpha is a multiple of this primitive polynomial. Let's prove that. Well, we know, this always comes from Gauss's lemma. We know that g of x is equal to f0 of x times q of x, where q of x has rational coefficients, as the ideal generated by f, which is the same as the ideal generated by f0, is the full ideal of polynomials in q of x vanishing at alpha. The polynomials in q of x that vanish at alpha form an ideal, and it's generated by the irreducible polynomial satisfied by alpha, which is our f of x. It's an irreducible polynomial, so it's the polynomial of smallest degree satisfied by alpha. So it generates the ideal of all polynomials vanishing at alpha. So since this polynomial has got integer coefficients, it certainly has rational coefficients, it's in that ideal, which means it's a multiple of f0 by some polynomial with rational coefficients. Write this in its primitive form, namely write this as f0 times the content of q, let's call it d, times q0, where this is now primitive. We can do that for any polynomial with rational coefficients. Regroup the terms, so this becomes d times f0 times q0. By Gauss's lemma, this is a primitive polynomial, right? And now we have an expression for g as a content times a primitive polynomial, but g was supposed to have coefficients in the integers, so its content is an integer. G of x is in z of x. The content is in z, which implies that q, which was d times q0, is in z of x. So the factorization that we knew about over the rationals actually takes place over the integers, and since f0 had a non-monic coefficient, any multiple of f0 has a non-monic coefficient, so there are no monic polynomials satisfied by alpha if f isn't equal to f0. Okay? So this is a useful test for something being an algebraic integer. And now we're going to apply this test, and we're going to start with a bigger piece of chalk. We're going to do an application. We're going to determine all algebraic integers in the field q square root of d, q plus q square root of d, where d is an integer. And we might as well assume, since we're taking square roots and we can modify d, that d is square free. So its prime factorization only involves primes to the first power. No squares in d. If there are any squares in d, you could just pull them out when you're taking the square root anyhow. So we're going to start with this field, where we take the square root of a non-square. You get a nice field which has dimension 2 over the rational numbers. This is the same thing as q of x modulo x squared minus d. It's dimension 2 over the rational numbers. It's a field because this polynomial is irreducible. And we're going to determine which elements here are algebraic integers. Which of them satisfy polynomials with... Now we know that every element of z plus z square root of d is an algebraic integer. I'm going to show you that right now, that every element of this form is an algebraic integer, but sometimes we're going to get more, like we saw for square root of minus 3. We'll get some surprising algebraic integers that we wouldn't have recognized. All right? So we're going to use this criterion, so I'll keep it up. First of all, why is everything of the form a plus b squared of d, where a and b are integers, an algebraic integer? I have to write down a polynomial it satisfies. A plus b squared root of d, let's call it alpha, satisfies the quadratic polynomial. Well, I'll write it like this. X minus alpha times x minus alpha prime, where alpha prime is the a minus b squared of d. Let's see why that's a... Let's see how that works out. It's nice. When you multiply this out, you get x squared minus, and then you get alpha plus alpha prime times x. But if you add alpha to alpha prime, you just get 2 times a. And then you have to multiply alpha by alpha prime. But if you multiply alpha times alpha prime, the square roots again cancel out, and you get a squared minus db squared. So any alpha in this field satisfies this quadratic polynomial with rational coefficients. Right? Because if it's in the field, a and b are rational numbers. If it's in this ring, a and b are integers, and we notice that the coefficients of the polynomial are also integers. Right? Sure. Any element alpha, a plus b squared to d, which lies in this field, so it means a and b are rational numbers, satisfies this polynomial, this quadratic polynomial, with rational coefficients, because the coefficients don't have square root of d anymore in it. I've carefully arranged by choosing x minus alpha times. This is a polynomial which you don't think of as over the rational numbers. This is a factorization of the polynomial in that field. But over the rational numbers, you get a quadratic polynomial. It might be irreducible, it might not. But anyhow, it has rational coefficients. Because if a and b are rational, d is an integer, these are certainly rational numbers. So everything satisfies a monic polynomial with rational coefficients. Okay, if it's in here, right, it satisfies a polynomial with integer coefficients. Okay, so if this polynomial is irreducible, and this is irreducible, I should say this is irreducible if b is not equal to 0. Because if b is not equal to 0, this number is not a rational number. Someone has a telephone call. So if b is not equal to 0, we see that this number is going to be an algebraic integer only when 2a is an algebraic integer and this is an integer. Sorry. So for b not equal to 0, alpha is an algebraic integer if and only if you have the two conditions, 2a is an integer and a squared minus d b squared is an integer. If b is equal to 0, then alpha is equal to a is an algebraic integer only when a is an integer, because in that case we have a rational number. If this polynomial isn't irreducible, that means that it has a rational root, and the rational root will be alpha. And so we've seen by the previous argument that the only rational numbers that are algebraic integers are the integers. Now, if you think about it, this also works for b equals 0, because it says if b is equal to 0, it says that a squared has to be an integer. Well, the only way a squared can be an integer is if a is an integer. Correct? If you have a prime in the denominator of a and you square it, you still have that prime in the denominator. So we can now erase this condition. We can, or just put it in quotes or something. You don't really need it. So alpha is an algebraic integer in q squared to d if and only if the coefficients of it, this a and b, which are a priori rational numbers, satisfy these two conditions. And that's certainly true if a and b are both integers, but we may get a little bit more that satisfy that condition, and we're going to now find out what does it. Okay, so now we're going to work out when do a and b satisfy these conditions. Remember, alpha is a plus b root d. So there are two cases. If you look at the first condition, it says that 2 times a is an integer. Well, it can either be an even integer or an odd integer. If it's an even integer, a was already an integer. So let's do that case first. Case 1. A is an integer. Well, that means that b squared times d is an integer. Now, I claim that implies that b squared is an integer, because d is square free. So if you had any prime in the denominator of b, when you squared it, p squared would be in the denominator of b squared and could not be canceled by the prime in d. Okay? And since b squared is an integer, that implies b is an integer. So in case 1, when a is an integer, b is an integer, and we're just back to the numbers that we already knew were algebraic integers. Nothing new was found. Because this is an integer. Once a is an integer, a squared is an integer. Oh, no, of course, I should have said that. Sorry. Since a squared minus b squared d is an integer, then this is an integer. Okay? We're combining the two conditions. All right, now we're going to do the second one. This is much more amusing. Case 2. A is in 1/2 of the integers minus the integers, i.e. 2a is an odd integer. So here a wasn't an integer, but 2 times a was. Okay, so let's write 2 times a is m. Remember, it's odd. So then I get a squared is 1/4 of m squared. Okay? So therefore, 4a squared is an integer. So I find so 4 times db squared is an integer. So I can write db squared as 1/4 of n. I think that's the notation I want to do. And I claim that this n is an odd integer. And the reason is, well, 4a squared is an integer, so since 4 times this is certainly an integer, that shows that 4 times db squared is an integer. So db squared is an integer divided by 4, but I claim that that integer n has to be an odd integer. And the reason is that this difference has to be an integer. And here I have 1/4 of some odd square, and I have to subtract off this to get an integer. Now if n were even, this would just be 1/2 times something, and I'd have nothing to cancel the 4 in the denominator. Right? If for example n were divisible by 4, so this was actually an integer, then you couldn't subtract this and get an integer, because this is certainly not an integer. It's got 4 in the denominator. So this also has to have 4 in the denominator, which means that n has to be odd. Okay? Now I claim that means that d is an integer, but we don't know about b. I claim that means that b squared, b is I don't want to write this. All right, why not? Yeah, b is 1/2 of n0 with n0 odd integer. See, d is an integer, so the only way this could have a 4 in the denominator is if b had a 2 in the denominator. B squared would then have a 4 in the denominator. B has to have exactly 2 in the denominator. It can't be an integer, and it can't have anything else in the. And so b is of the form 1/2 n0 with n0 an odd integer. We're not done yet. We're not done yet because we still have to check that this thing is an integer. So let's write now down what that looks like. A squared is 1/4 m squared. So a squared minus db squared is 1/4 of m squared minus d times 1/4 of n0 squared. And that has to be an integer. In other words, this is 1/4 of m squared minus d n0 squared must be an integer. Which means that this number in here has to be divisible by 4. m0 squared, m squared minus d n0 squared, congruent to 0 mod 4. That's our final condition. Now, look at this. This is an odd number, so its square is congruent to 1 mod 4. Same thing with n0. So this shows that you have to have d congruent to 1 mod 4. Namely, you can't do this for every d. The only way you can get extra algebraic integers where a and b are not both integers would be to have a half integer, b a half integer, and d congruent to 1 mod 4. It works. And that's what happened in the case that we looked at, this number minus 1 plus the square root of minus 3 over 2. This is the case where a was minus a half, and b was a half, and d was minus 3. And minus 3 is congruent to 1 mod 4. So if you have all these conditions, and d is 1 mod 4, then you can arrange this to be an integer and this to be an integer without both a and b being integers. So you get extra algebraic integers. All right? So let us regroup and summarize what we've got. Let's go over here. So here's our summary. So d is a square-free integer. So the algebraic integers, if d is congruent to 2 or 3 mod 4. By the way, d can't be divisible by 4 because it's square-free. Right? If it were divisible by 4, it's got 2 squared in it. So the remainder after division by 4 is either 1, 2, or 3. If it's 2 or 3 mod 4, then the algebraic integers in q squared of d form the ring z plus z square root of d. That was simple. 2, if d is congruent to 1 mod 4, the algebraic integers in q squared of d form the larger ring ring z plus z times the element 1 plus the square root of d over 2. Because this is in a case where a and b are half integers, right? And if you multiply this by 2, you can get the element square root of d, so you can get all the things in case 1. So if you just adjoin this element, which is an algebraic integer, then you get the large ring of algebraic integers. So in most cases, you just get exactly what you thought you'd get, the simple integer multiples of 1 and square root of d. But when d is 1 mod 4, you get a slightly larger ring of algebraic integers. That's what we've now shown. OK, now, it turns out that it's best not to index these rings by this square-free integer d. It's best to index it by the discriminant of the irreducible polynomial satisfied by the element that you're adjoining. So let's see what the irreducible polynomials are. Yes?
When you say to index the ring, are you talking about?
Well, namely, it looks like we've got a ring now for every square-free integer, right? Which is analogous to the Gaussian integers, which would be the case d is equal to minus 1. Now, for every square-free integer, square root of 2, square root of 7, square root of minus 7, we have now a ring. Sometimes it's the stupid ring, and occasionally we get this larger ring. So I could say that ring was indexed by the number d. Namely, for every d, I had such a ring. But it turns out there's a slightly different invariant that I want to use. It's a multiple of d, which you're going to see. Yeah?
How would you write the integers in Q? Like, how would you get that? Just say it, or just...
How would I write this?
No, how would you... The integers in Q of d, like the symbol for that.
Oh, just call it, I don't know. You mean you want a ring? Call it R.
Okay.
Yeah, I mean, it could be the ring R. How's that? And then we could call this field F. So I could call this RD maybe, or something like that. Okay? But I want to use something different than D to index it. That's what I just was saying. Was that your question? Okay. You need a name for it. From now on, it's called R. Okay. Now, the polynomial satisfied by square root of d is this polynomial, x squared minus d. Its discriminant for a general quadratic polynomial, the discriminant is b squared minus 4ac. Right? The discriminant here would just be 4d. Correct? Okay. Now the polynomial satisfied by 1 plus the square root of d over 2. Let's take a look at that polynomial. That's more interesting. That looks like x squared minus x plus, and then you have to multiply this by its conjugate, and that gives you, I believe, d, 1 minus d over 4. Now that doesn't look like it has integer coefficients. But in fact it has integer coefficients because remember this d left a remainder of 1 after division by 4. So this difference is divisible by 4. So that's got integer coefficients. What's this discriminant? Well, what's its discriminant? Well, you have to take b squared minus 4 times this. So b squared is 1, right? Minus 4 times this, which is 1 minus d. Well, its discriminant just turns out to be d, not 4d. And we're going to use that number to index the ring. So we're going to call this capital D, and we're going to call this capital D. So here the discriminant is 4d. And here the discriminant is just d. And it's this number, it's this integer we're going to use to index these rings. So notice this number is not always square free. But it has the following property. The discriminant has the property, and as again, you have to do this a little bit to realize why it's better to go to this capital D to index things. But D has the following property. A, it's an integer which is congruent either to 0 or 1 mod 4. You see, in this case, it's congruent to 1 mod 4. And in this case, it's congruent to 0 mod 4. Right? And 2, D is as square free as possible given condition A. As square free as possible given condition A. Namely, the only prime such that the second power can divide it is 2. And the reason is you have to arrange in the first cases for the discriminant to be divisible by 4. You see, these things aren't divisible by 4. In this case, you'll find the discriminant, the capital D, is divisible by 8. And in this case, you'll find it's exactly divisible by 4. But no other primes can divide the discriminant. And we're going to list these rings according to their discriminants, capital D. So I'll give you the examples. So it's very easy to just go through the numbers, which are 0 and 1 mod 4, and see the ones that are as square free possible given this condition A. So if D is less than 0, you say R is an imaginary quadratic ring. And if D is bigger than 0, you say R is a real quadratic ring. And the reason imaginary and real come in is if you're taking the square root of a positive number, then you can do it in the real numbers. And if you're taking the square root of a negative number, you have to use the imaginary numbers. So let me list the D's which are less than 0 that satisfy this condition. -3, -4, -7, -8, -11, -12. Does -12 get listed? Well, it's divisible by 4. But if I divide it by 4, I get to -3, which is a permissible discriminant. So it's not as square-free as possible given condition A. So it's not a discriminant. So the next one becomes 12. Then what is next? 15. Is -16 good? No, -16 is no good, because if I divided it by 4, I'd get something here. So that's not on the list. Then I get -19. How about -20? Sure. -20 is divisible by 4, but if I try to divide it out by 4, it doesn't satisfy this condition, because I get -5. So it's as square-free as possible. And then -23, etc. So you get all those negative numbers. And D bigger than 0, you get the rings where, by the way, this is the Gaussian integers. This one is Z of I, right? Because I squared is -1, so the discriminant would be 4. This one is the ring that Euler discovered, that's Z of x modulo x squared plus x plus 1. D greater than 0, the first good discriminant is 5, because 4 doesn't work. 8, because, yeah, congruent to 1 minus 8. 9 is a square, so that's no good. So the next one is 12, 13, 17, 20 is 4 times 5, so it doesn't work. So then 21. Then 24 is 24 work here 4 times 6, yeah, 24 works. 27, 28 is 4 times 7, so that's fine. 29. So you can make a listing of the numbers congruent to 0 and 1 mod 4 that are as square-free as possible. And for every one of these numbers, we get a ring. We get a ring, and the ring is here. So there are an infinite number of rings that are analogous to the Gaussian integers, and we now have the fun of playing with them. And we're going to play with them until the end of term. Now, I should say that you could spend the rest of your life playing with these rings. People do. I mean, this is serious stuff. So, for example, a big question which Gauss asked, a huge question which Gauss asked, is which of these rings have the property that every ideal in them is principal? Every ideal is principal. The Gaussian numbers did, so we can circle this. This is a Euclidean ring. We can circle that. Okay? So on this list, Gauss made a very good guess. And he guessed that this one, this one, this one, this one, this one, this one, and 19, and 3 more. -43, -67, and -163. 1, 2, 3, 4, 5, 6, 7, 8, 9. Those 9 rings had the property that every ideal was principal and the others didn't. That was proved in the 1960s. All right. Gauss also guessed that of these rings, the ones with positive discriminants, there were an infinite number that had the property that every ideal was principal. He couldn't say which ones, but there were an infinite number. That still has never been shown. In fact, of these rings, in some sense, about 97% of them should have this principal ideal property statistically, and no one can prove that they're even an infinite number. So that's what I mean about this being now a subject which is actively investigated mathematically. So we're going to focus our attention on this case, the imaginary quadratic rings. They're much easier. For a reason I'm now going to, well, I'll just tell you why they're easier, and then we'll pick up with this next time. So the first thing you want to know about rings before you start doing ideals and principal ideals and everything is, what is the unit group? What is the unit group? So in the Gaussian numbers, we found the unit group was a finite group of order 4 generated by I. So if d is less than 0, the unit group is a finite group. It has order 4, and for d less than minus 4, it has order 2. In fact, in this case, r star is the same thing as z star, as plus or minus 1. So the units are very easy to determine in the imaginary quadratic case. I'm going to start with that next time. However, in the real quadratic case, r star is an infinite group. Always. Always. So already the units are a difficult situation to deal with. And in fact, that complicates all kinds of questions of deciding whether ideals are principal or not. In every one of these cases, the unit's an infinite group. In all of these cases, once you leave these two, you don't get any more units than you had already in the integers. So we'll start with that next time. And the next 3 lectures are going to be an investigation of the ideal theory of these rings of imaginary quadratic integers. Okay?